Hi Lucas, do you have a moment?
Sure.
Okay, so I just got a call from a teacher in high school and she's teaching programming to 25 pupils in one class, and she always has the issue that these pupils get stuck and then she has to go around and help everyone, but they cannot proceed on their own. So maybe we can create an automatic system which can give actionable feedback to these novices so they can proceed on their own?
Yeah, I think that's possible. We can start from the work of Sing et al.
Sing et al. Develops Autograder, a tool which can give feedback on logical errors in programming exercises. A program is first translated to the Sketch program synthesis language together with a set of rewrite rules, which are handmade for the given assignment. Then the Sketch synthesis system figures out which of the rewrite changes are needed to make the program correct, and finally feedback can be given.
Okay, that looks very promising. The teacher also mentioned that more than half of the errors are syntax errors. So not only semantic but also syntactic errors.
I will have to look into that because Sing et al. Does not support fixing syntactic errors.
Okay, so yeah, it's very important to support these as well. You might have a look at TreeSitter, which is a parser which also supports parsing source code with syntax errors.
I'll look into it.
Okay.
Give me a couple of months.
Great.
Hi Jesse, do you have a minute? I want to show you my progress on the automated feedback system.
Oh, great. Yeah, please elaborate.
Our architecture is based on Sing et al., but with a new first step. Syntax errors are fixed by detecting them with fault-tolerant parsing and applying simple rewrites automatically. Afterwards, for syntactically correct programs, feedback on logical errors can be given in the same manner as in Sing et al., but we've made a new implementation and added some additional features. Here we'll show an example of our approach for fixing syntax errors. In this code, the last line has a syntax error as the two arguments of the print call are not separated by a comma. This program can still be parsed by TreeSitter, which is a tool that can generate a concrete syntax tree for programs despite any potential syntax errors. When it encounters an error, it adds an error node in the tree. It is added around the identifier z, which is also shown in the tree. To fix errors, we've created simple rewrite rules which identify a specific location in the syntax tree using a query and an error type. The error type denotes where the error is expected in relation to the query. After a location is found, a list of fixes can be tested. In this case, the query looks for an argument list node, which is found in the print call. And the error type specifies that the error should be the child of the argument list, so the error at the identifier z is found. In this case, the first fix adds a comma after the z, but this wouldn't be correct. After applying a fix, the code is parsed again, and we can detect that the error hasn't been fixed. The current fix is then undone, and the next fix can be tested. The next fix adds a comma before z, and this is actually correct. We can see in the syntax tree that the error has been resolved with this fix. By creating a list of rewrite rules that fix specific errors, we're able to correct the majority of syntax errors in programming exercises, and it's easy to add more rules and improve the system even further. However, this approach does not work well for indentation errors. TreeSitter cannot easily detect indentation errors and is often too lenient when it comes to parsing indentation in general. Because of this, we've created a separate approach for fixing these errors. This new algorithm can keep track of correct indentation and then fix mistakes. For example, it can remove indentation where it shouldn't be, like in this case in front of the print statement. To make sure that the indentation of an else statement is correct, the algorithm can match the level of the else to a previous if statement. It also correctly adds indentation after keywords like if and else. As we've mentioned before, our approach for fixing logical errors is based on Sing et al., as it can generate actionable feedback for fixing logical programming errors. During the translation step, rewrite rules are inserted into the submissions of a student. These rewrite rules are handmade and specific to the assignment. They consist of potential changes that might fix the program. The Sketch synthesis system then decides which of the potential rewrites are necessary to make the submission correct. To check that the new program functions correctly, the model solution is also translated to the Sketch language and is used in the synthesis. In the final step, the synthesized program can be used to generate feedback on which changes are necessary, and we can give this feedback to students. We'll further explain the technique by showing an example. For this assignment, the student should write a function that takes a number as input and returns a positive number as is, but for negative numbers it should return 0. The current code is incorrect as 1 will be returned for negative numbers instead of 0. Two rewrite rules are given here. The first one replaces a return with a return 0. The second rule replaces an equality with a greater than 0. Only the first rule is applicable in this specific submission, and it is applied to both return statements. It is important to note that the original values before the rewrite are kept as an option and that the rewrites are only potential changes. In the next step, the program is translated to Sketch. To correctly give feedback, the functionality of Python needs to be emulated in Sketch. The two languages can differ quite a bit. For example, in Python, a variable can have values of different types, while in Sketch this needs to be emulated with a multi-type struct. This struct can then act like different types, as is also done in Sing et al. Operations on these multi-types had to be added in Sketch, and a lot of standard Python functions too. The code on the left shows the translation to the Sketch language and also one of the rewrite rules. The code for the rewrite rule contains two question marks, which are filled in during synthesis to either apply a rewrite rule or not. During the execution of the Sketch synthesis, all the different changes are tested efficiently and the cost is minimalized. In the case of Sing et al., the amount of applied rewrite rules is the cost that they try to minimize, while our approach uses custom costs for different rules to allow different priorities for each rule. Based on the output of the synthesis, we can automatically generate feedback on which changes are needed.
Okay, this looks really promising. And does this also work on real submissions?
Yes, it does.
Here is a complete example of the feedback our tool is able to provide. The assignment for this example is to write a program that asks the user to give their preferred temperature and then prints a holiday that fits with this temperature. The code contains syntax, indentation and logical errors. In the elif statements that are shown here, there is an extra colon after elif, which is a syntax error and needs to be removed. This is given as the first two lines of the syntax feedback. The last two lines of the code contain indentation errors. They both need to be dedented once. For values 5 and 15, the current program would not print anything, while of course a holiday should be printed. The greater than signs are replaced with greater than or equal according to the feedback, so that the correct holiday is printed for these values, just like in the solution. The feedback shown here as text is an example, but isn't necessarily what should be shown to the student immediately. It might be more interesting to show hints that don't spoil the solution first, which can of course be generated based on the info from our system.
Let's first take a look at programs with syntax errors.
We've tested our system on 5 different assignments on the eTeacher platform. This is a platform that is being developed at our university to teach programming to high school students. Our tool is able to give feedback on syntax errors for 71% of the more than 700 submissions that contain syntax errors. In addition, for 34% of these submissions, logical feedback can also be given. We did encounter an issue, which is that in 6 to 12% of cases, Twister is too lenient and does not always detect all syntax errors. We can check that not all syntax errors are fixed by parsing the code in Python, and in those cases we are not able to give feedback.
Let's now have a look at all incorrect programs with and without syntax errors.
When we include results for all incorrect programs, we are able to give full feedback for 64% of all incorrect submissions. So syntax and logical feedback for programs with both errors and logical feedback for programs with only logical errors. This is a set of 4,735 submissions. So some assignments, like the assignment called capitalize, the unknown variable error occurs often. This occurs when a variable is used but was never declared. This is not a syntax error and is also not allowed in Sketch, so it can't be fixed as a logical error either. The submissions in the category no solution found are currently not getting feedback because the handmade rewrite rules for the assignment don't fix the logical mistakes, but it is possible to expand the rewrite rules and give feedback on these programs with our approach. Our tool assist is able to provide feedback on at least as many or more submissions compared to existing tools that can provide actionable feedback on how to fix a program. Autograder is the tool of Sing et al. On which our approach is based. This tool is not able to give feedback on syntax errors, so it performs badly when giving feedback on a dataset of all types of incorrect submissions. Praet et al. Expanded the methods of Sing et al. By first fixing syntax errors using recurrent neural networks. Their approach only fixes syntax errors and does not generate feedback for them. It is also important to note that the statistics can't really be directly compared, as the tools and datasets for Autograder and Praet et al. Are not publicly available.
Okay, so this seems to work quite well, but is it fast enough to use in class?
Let's have a look.
We can give feedback in 2 steps. The first step fixes syntax errors, which can be done quickly and takes on average 100 milliseconds. The feedback on syntax can then already be given. The feedback on logical errors is slower as it uses program synthesis. On the graph, we've shown the time taken for logical feedback. On average, we're still able to give timely feedback in a few seconds. The slowest average was for the assignment holiday and is 7.3 seconds. In blue are the submissions that receive feedback, and in red the submissions that did not get feedback. The outliers are typically programs that can't get feedback. The programs that fail immediately give an error at the translation step or during the first checks before synthesis, while the slowest programs are the ones for which all possible combinations of changes need to be tested before failing to find a solution.
Okay, this seems very usable. So what are the new parts of your approach, and which limitations are there in your approach?
Good question.
We've used a few novel ideas to give better feedback on a larger variety of errors. Our approach uses a completely new technique for fixing syntax errors. By detecting errors using fault-tolerant parsing via tree-sitter, we can correctly detect the type of syntax error and fix it via a set of rewrite rules. For logical feedback, we've made a new implementation based on existing ideas, but we've expanded the strategy and added new features to allow more functionality. For example, print and input functions can be used and translated to Sketch, which is very important for introductory programming assignments. Both need to be emulated in a new way, and input uses the concept of uninterpreted functions to mimic the possible inputs of a user. Additionally, during translation, Assist keeps track of defined variables, and these can automatically be used in rewrite rules without needing to know the name of the variable. For example, when a user forgets to print the result, this can be inserted with a rule, even when they didn't name the variable something obvious like the word result. For each rewrite rule, a custom cost can be defined, which is useful to set different priorities for different rules. For example, if the goal of a program is to print the word 0 when the input is the number 0, then it's useful to have different fixes for the two programs shown below. The program on the right is fixed by a rule that can give general feedback when the entire if structure is missing, and the program on the left is fixed by a rule which gives specific feedback on how to fix the condition in an if statement. In the program on the left, it could technically be correct to fix the program by inserting the entire missing if statement, but this wouldn't really be useful for the student, as they already have an if statement, but with a condition that is always false. When all rules have the same cost, the synthesis system considers both fixing the condition and inserting the correct if statement to be worth the same. By giving the more general rule a higher cost, we can make sure that more specific feedback is given in the correct situation, but that more general feedback is still possible as a fallback. Our approach does have some limitations. Tree-sitter does not parse programs in exactly the same way as a Python interpreter, and it can sometimes be too lenient. One example of this is in indentation errors, as we've explained earlier, but there are other cases as well. For example, using the expression for tuple unpacking on the right side of an assignment does not generate an error in tree-sitter, but is not actually allowed in Python syntax. Some error types are not able to get feedback, like for example the undeclared variable error, as it is neither a syntax nor a logical error. However, this error can still occur often in some assignments, as we've shown in the statistics. Our goal is to give minimal feedback so that there is no redundant advice, but this is not always possible, especially when combining syntax and logical feedback. In the example shown here, the last print has a syntax error because there is only one quotation mark. One approach to fix this is by adding a quotation mark after the word result. After applying this fix, the logical feedback generates two changes. The first one is to remove the entire print statement as is incorrect, and the next one adds the correct statement, which is to print a variable called result. In total, this approach requires 3 changes, while just removing the first quotation mark would have fixed the problem in 1 change. At this moment, the syntax corrector only generates the first correct fix that it finds, even when multiple fixes might be possible. There are also cases where the given feedback might not be enough for a student to understand what they did wrong. Here we show an example of feedback that might confuse a student. In this code, the student uses the condition that the length should be greater than or equal to 0, but this will always be true. The print statement that the student added in the else statement is unreachable. The feedback here is to add the missing condition to print empty string, but the student might think that they've already done this and the current system doesn't give an explanation as to why the current print is incorrect.
Okay, so it seems that the system is usable. I will let the teacher know.
Sounds good, but first we would have to figure out what the best approach is to present our feedback to students.
In the future, it would be interesting to conduct a user study to determine how to best give feedback to students. Our tool is able to detect which changes are needed to fix the student's submission, but giving this information immediately might not help in improving the student's ability to code. Figuring out how to best apply the information that our system Assist is able to provide is an important next step. An interesting initial form of feedback might be to first give information about how many changes are necessary to fix the program, or to indicate where the mistakes are located in the code. Additionally, the tool itself can be improved. The current approach for fault-tolerant parsing still has some flaws, as it can be too lenient and doesn't detect all errors correctly. This can be improved by making the Python grammar of tree-sitter fit better to the real Python language. Another way to improve the system is to add static analysis, which could help for giving feedback on problematic error types like the undeclared variable error, and for detecting things like unreachable code. Lastly, it might be interesting to let the syntax and logical feedback systems communicate more to make the overall feedback minimal. This could be done by keeping track of the different ways to fix the given syntax errors and find the best ones for further logical feedback.
Thank you for listening. Are there any questions?
Okay, great. It looks like we have about 3 minutes for feedback. So, do you want to?
I'm just carrying the mic.
Thank you. So, can the next speaker maybe start getting? Actually, no. So, do we have the next person start getting set up while we do questions? Yep. So, the next person should start getting set up, and then.
Hey, thanks for that. Very cool talk. So, from my limited experience of teaching Python a while ago, I remember like tutoring people and having to explain that like if you see an error in the Python interpreter, the error might actually be on the line before or the line after, or it's not always clear where it is. I was wondering whether you think like your approach for the syntax checker, is that specific to the assignment context, or do you think that could make a better feedback for Python interpreters in general?
I think for now it's best to use it just to fix like simple syntax errors, as I don't know how it will. It fixes the errors locally, so I don't know if every syntax error is easily translated to the correct line. If you're looking at it from the syntax tree, it might be hard to fix every single syntax error the same way.
Question/suggestion. Have you looked into Rough's parser to handle like fault-tolerant parsing, and it may be able to give you fewer errors, and so you would be able to remove that 6-12% of problems that you have with Tricitor?
I haven't heard of that yet, but I'll try to check it out.
Oh yeah, so it looks like we have time for one more question. So I think every approach has its limitations, and with a feedback system, there's always going to be some that work better and some that struggle more. And I know you talked about these limitations in the paper, but could you maybe summarize for all of us once again? Maybe what is the error where you feel like you really succeeded? This is the kind of error we're handling really well. And what is the one kind of error where you're like, this one's still really hard, this one we want to focus on in future work?
I think in this case, one of the errors that we are not able to handle, which we probably should be able to handle because it occurs often for students, is where they can have like specific errors, like the variable, when a variable is used but never declared. Our tool is just not able to handle that at all. Well, that's something that students might do often. What a tool is really good at is fixing specific logical errors as small mistakes in, for example, a condition, or adding missing parts to a student's code. Those types of things where the student has the right idea about how to do the problem, but they might have made like a small logical error, or even, of course, syntax errors as well.
Great, thank you. It's a great response. So looking at the time, I think we'll call that it for questions. Can we get another round of applause for the speakers? Great talk.